Hyvää iltapäivää. Good afternoon, ladies and gentlemen. I am Marja Sakari. I'm the director of Atheneum, and it's my pleasure and honor to welcome you here to the Virtaa klubi. Virtaa, which means to flow. So this is an interdisciplinary club or happening event that has already been for 20 years, and the initiator of this event is Minna Pöllänen, pianist Minna Pöllänen, who has in all these events she has combined music with different areas like philosophy, science, art, visual arts, and so on and so forth. So I wish you a very interesting afternoon, and welcome Minna Pöllänen.
Welcome, Frank Wilczek and Betsy. It's really wonderful to have you here again. Last time we talked about Mozart, and that's why I wanted to play Mozart to sort of connect these two events and to show how close they are. I promised to tell you about number symbolism in Bach's music, and there will always also be a conversation with Frank, so I thought we might combine the two. And Frank might come here and present some nice comments if he likes. But he doesn't have to. No. Yes, you see, Frank is many things. Sorry. Frank is many things, but he's really a humorist. Maybe that's why he's coming into my events. Yesterday we had a very nice small talk where I was telling what I'm going to talk about, and basically I was talking about number 1 and Pythagoras, and Frank said, "I'm learning something from you." So I think that's a really good joke.
I didn't say what I was learning was correct, though. No.
Okay. So we want to today to go back to the times when the world was one, and science was called natural philosophy. And here we have a picture where we have the 3 kinds of music in medieval times, and that there is called musica mundana. It's the harmony of the world. The one underneath is musica humana, and this is the picture of the harmony between people. People are nothing alone. We need counterpoint, we need polyphony, right? To really have meaning in our lives. And then down there it's musica instrumentalis, that's sort of like very low kind of music. Then it still was. Only in the 17th century it really got to be respected like vocal music. Okay, then next picture. This is King David tuning his harp. And there you see God is giving the proportions. Here are these bells, and they are finding the harmonies there. Why I'm showing this? Because this is a typical first page of this, what do you call this, illuminated manuscripts? Yeah. So they always used proportions of octave to the 5th. This bigger part of the B and the small part together, they make an octave. So everything in art was kind of taken from the musical proportions. Oh no, where do I do this? Just like in architecture, here's a church where you have do, re, mi, fa, okay? Yeah. And you know that Palladio's Quattro Libri di Architettura, it was all taken of music theory, all the proportions. And who was responsible for all this? This guy named Pythagoras, who is here ridiculed because he didn't like to eat beans. You know, yes, it was fava beans. That was the only kind of beans they had in those times, and we don't really know why it was, but I'm sure the Romans were so far away from what Pythagoras was doing that they just saw the funny side of this side of Pythagoras. There are 2 sides of Pythagoras. He's the father of music and father of mathematics. Wasn't he the first really pure
mathematician, at least in the... Yes, I would say so. He he and his school are credited with, I would say, the first fundamental, surprising theorem in mathematics about the different sides of a right triangle and their quantitative relationship. And although Babylonian mathematicians and Egyptian mathematicians had looked at special cases of this general relationship, the idea that there could be a general relationship and that you could prove it, that was so important to the future of mathematics and science, really came from the Pythagoreans.
But he did many other things besides that triangle. I show you something he did, which I absolutely adore. Well, here are the overtones. Does somebody not know what the overtones are? The harmonics or partials? Yläsävelet. Because I can show how it sounds, okay? This is so amazing. Every tone you play, it's not just this tone. It's, let's say we have this, it's this, and then this, and this. They all sound together. We just don't perceive them. We perceive them as color, but not as partial sounds. And it makes major chord. And these are the... Maybe you can tell.
Well, now, of course, nowadays you can hear, in computer music, you can hear pure tones, and it sounds quite different and much less rich than when you have a vibrating string. It vibrates when you pluck it in several different patterns simultaneously. So really you're hearing a kind of chord, and the different musical instruments make different chords, and that's why they have different sounds, different textures.
So here we have the basic sound. Then if we put like finger and a violin string in the middle, we will get the octave sound. And then 1/3, it's the 5th, 4th, major third and minor third. They are all numbers. And the smaller number, the more consonants, the more harmonious it is. Okay, let's go quickly so we have time for... Okay, so this is something maybe you don't know about Pythagoras, how he explained, how he got into these numbers. He said everything is number. He thought that point is the essence of a circle, which is beautiful because also, like in Kabbalah, they explain that God created the world by condensating himself into a point that was so heavy that he had to explode. So, and this is the circle starting to reflect on itself. So both these circles touch the middle point of the other. And this is a very important symbol, like in churches. It is called a fish bladder. But it's also vulva. It is the creation. It's the feminine symbol. And then he got all the numbers with the same method. This is number 3. He just took lines and combined these middle points of the circles. And then he ended up to number 10, which is the very, very sacred number also in the Kabbalah. It's like 4 plus 3 plus 2 plus 1. And the interesting thing is that Kabbalah has the same thing, only they picture it differently as a 3. So I'm talking about this because for Bach, number 10 was very important. He put it, like in this C-sharp minor fugue, the theme comes 10 times, and in many, many pieces he has symbolism related to like the 10 commandments, and it's also the 10, let's say, words by which God created the world, according to Kabbalah. Okay. So this is the tree of life, which actually was inherited from the Assyrians. I had this evening once, I had Simo Parpora, who is a very well-known Assyriologist, and he explained that the Assyrians, they had 360 degrees, because all their gods added together were 360. And okay, but this is very much related. I cannot go into it now. If somebody's interested, I can tell you where to find things about it, but it's extremely interesting. Okay, let's go back. So here is the Kabbalah, same 1, 2, 3, 4. Does somebody know what this lowest row means? Okay, it's Hebrew name for God, Yod-He, Vav-He. And it's male symbol, feminine symbol, male symbol, feminine symbol. And these 72, it's 72 names of God. And accidentally, you see all these, I'll explain immediately, but because the alphabets have also numerical values. And it's not just a game, they really, like I will show you right now, but 72 is also the numerical value of the word nature. So Spinoza got it from the Kabbalah, because he said God equals nature. I think that's very interesting. Of course, he denied all this tradition, but he went to these schools, he learned these things as a child. Okay. So this is, I think this is like a paradox. I think one very good definition for paradox is it's a truth that's standing on his head to attract attention. This is Outi Heiskanen's picture of a tree. You said it's like the human nervous system. But this inspired me to do this evenings about the trees, because I love trees, but we did it with Outi together, and then this Assyriologist, and it was really, so I show you the tree because I'm going to tell you my image of Goldberg variations. I think it's also like a tree later. Okay. So this is a book that recently appeared. This woman did a really enormous work. She wanted really to show that all this talk about Bach using number symbols is nonsense, because it kind of got out of hand because everybody was just counting measures and finding these meanings that were not there. But she actually, for her own surprise, found out that it is there. And that in Bach's time it was very commonplace to use both Pythagorean and Kabbalistic number symbols. And for Bach especially, it's the proportions, 1 to 1. So he went to a lot of trouble revising his works when he was older, to make them this perfect proportion 1 to 1 or 1 to 2. And also between big collections of work, for example, the Klavierübung 2 and 3, together they have counted so that they have the same proportions. Another thing that Bach used was his name, B-A-C-H. If you take those 4 letters, you have, so this is Bach, what Bach used. This is see, A is 1, B is 2, C is 3, and H is 8, so it makes 14. So he used that a lot. And the other one he used a lot was 41, and that was J.S. Bach, if you take his first 2 initials. And the very cute thing is that his wife, Barbara, his first wife, Barbara Bach, also made 14. So then when they got their children, they made sure that also their names, Wilhelm Friedemann Bach, Carl Philipp Immanuel, it was an E, also makes these numbers. So he must have loved numbers. Okay, so I just want to show you quickly, because I am so fascinated by these Hebrew letters, because they are not just letters, they are incredible packages of energies. And they have a lot of meanings. And this first one, Aleph, doesn't have a sound at all. It's emptiness. Its only sound is defined by the things that it's with. Okay? So this is like the first. Second one is Beth, which is like an open, this is the feminine symbol also. This is like the creation. So God and his creation. And then we have Gimel, which I think is very beautiful. This is really an image of Trinity. It kind of combines the first and the second. So it's like Plato's philosophy. And then we have Dalet, etc., which is like, again, a female symbol. And so on. It's an incredible, you can go crazy if you start studying this, these Kabbalistic meanings, but I love it. It's wisdom also. Okay, so I think this is this is very bad picture, but just to show you how Bach's music is like waves. It's really nature. This is the first preludium of the Polteperites clavier. Okay, and let's finish with this, because this will link this talk to Frank's, right?
Yes. Thank you. Okay, well, this is a beautiful illustration of the fact that there are different ways of thinking about the same thing that can be very fruitful and illuminating, which is going to be my main theme. So welcome. It's really a great pleasure and an honor to be in this program with Minna and Irina, who are two wonderful artists and also great spirits. Today I'm going to be talking about complementarity. Complementarity is a concept that I've grown to love. It's an aspect of the human condition and also an aspect of physical reality. It's a concept that, if you think about it, if you internalize it, I think will enrich your mind and your experience and give you some kind of wisdom. So, what is it? Let me introduce the concept of complementarity through a passage from F. Scott Fitzgerald that I've rewritten as a poem, just by breaking it up into lines. It says, the test of a first-rate intelligence is the ability to hold two opposed ideas in mind at the same time and still retain the ability to function. So I'm sure you all want to have first-rate intelligence, and so let me cement that notion. So first, let's start with complementarity as an element of how we perceive the world. Many of you are probably familiar with this figure. It's a duck or a rabbit or both or neither. What is it? It's something whose complete description can only be obtained by viewing it in two different ways, two complementary ways. You can view it as a rabbit, and this becomes the ears, or you can view it as a duck, and this becomes the bill. Is it really the ears? Is it really ears? Is it really a bill? Well, it's both. And to do full justice, even to this simple figure, we need to be able to keep both ideas in mind at once, and the full reality is not exhausted by either view. That's kind of a tricky game, or a special example, but this is how we routinely process the world. The focus of our vision, where we have really good resolution and can see the details of things and their colors, is very small. It's basically like my thumb seen from this distance. And so to construct our vision of the world, we have what are called saccades. The eyes move around and move from one interesting feature to another, and our brain puts them all together. So when you're looking at this beautiful face, what you're actually doing is focusing on different parts and constructing in your mind the complete image. It's a very complementary process. You take one aspect at a time and then synthesize them. Artists, especially in the 20th century, tried to do justice to this aspect of our perception, of our mind. This is a famous picture, Guernica of Picasso, and you can see that several different perspectives are represented at once. So, for instance, this bull is seen from different perspectives, and this is, of course, an impossible figure as drawn, but you can imagine taking it in one piece at a time and then synthesizing it. You immediately realize it's a bull, and it's the artist is bringing out explicitly the fact that we focus on one aspect at a time and trying to show us, put that right in front of us. This is an example of complementarity that I got actually from Minna, that I think is very beautiful. Can we turn on the sound? We've lost. We must have switched computers or something. Just a second. Okay, let's try again. Oh, sorry. My phone. No. Well, it's a pity if we can't get this to work. It worked before, yes, indeed. Famous last words. No, we tell you, that would be an adventure. Yeah, we'll try one more thing and then declare victory. Oh, okay, maybe that'll do it. For some reason it switched. There we go. Bach always comes through in the end. So, Minna pointed out a very beautiful example of complementarity to me, which is that when you hear polyphonic music, you, at the same time, in the horizontal direction, in the musical score, you have melodies, and in the vertical direction, you have harmonies. And if you try to focus, you can sort of focus on the harmonies, or you can focus on the melodies. It's quite difficult to focus on both at once. Only a first-rate musician can do that partially, but that's done by rapidly synthesizing the different points of view. Nowadays, with computers, we have these beautiful visual representations of everything that goes on, and this, to me, really widens the experience of the piece. You can see and put our very powerful visual processing centers into the process of appreciating this composition. So I highly recommend these kinds of musical videos, which you can easily find on the web. And they're beautiful examples of complementarity. So that's what I wanted to say as a brief introduction to complementarity in perception. There's much, much more to say about it, and indeed about everything I'm going to mention today, but I hope that whets your appetite and convinces you that complementarity is a very important part of our perception of the world. Now I'd also like to mention a different aspect of complementarity in concepts. Mathematicians find it very, very useful and important, following the great discovery of Descartes, to represent equations also as pictures. The equation here that you see to a mathematician is equivalent, or can also be represented dually, if you like, or in a complementary way, as a sequence of pictures. You get a different picture for each value of b, and these curves are an alternate representation of the equations, and they suggest different kinds of questions, different kinds of insights. When do things bend? When do they break apart? Whereas and so it appeals to our visual processing centers, whereas the bottom representation, the mathematical, logical representation, allows us to do complicated logical operations smoothly, which would be hard to do on the figures. This fractal is another striking instantiation of complementary aspects, because it's a very complex figure, and if you're just given this figure, to describe its properties can be very, very complicated, and there are wonderful theorems about whether the gold pattern is continuously connected, for instance, and or does it have gaps? Very, very difficult and beautiful theorems are about things like that. But on the other hand, the rules that are used, and it's a complex and visually appealing aesthetic object, but on the other hand, the rules that are used by the computer to generate this figure are ideally simple. They're very, very simple mathematical operations repeated over and over again by the computer. And when you do this kind of iteration, very complex patterns emerge. And that's the secret of fractals. So this is showing complementary aspects of simplicity and complexity, and really making it very vivid that simple rules can lead to very complex results. The most famous example of complementarity to a physicist, and really how I first got most interested in this concept, is that it is actually a rigorous theorem, a feature of quantum theory that was especially emphasized by one of the great founders of quantum theory, Niels Bohr. In quantum theory, the primary description of a system, the primary description of reality, is in terms of wave functions. So systems are defined not as objects in space, but as wave functions, which tells you about their properties. So one thing a wave function tells you, for instance, is about the probability of the system being at different places or in different configurations. But a profound aspect of quantum theory is that we cannot and do not observe the wave function directly. It's kind of a primary description of reality, but we can't access it all at once experimentally. Rather, if we want to understand a system, we have to ask specific questions. We have to describe specific kinds of experiments or observations we would perform on the system. Observation involves interaction. To observe something, you have to shine light on it or somehow pass it through a filter or something in order to assess its properties, plug it into a meter, and that changes the object in general. An observation will always, at some level, make changes in the target of the observation.
Does that mean that the observer and the observed thing is one? Yes.
You must treat the observer and the observed as a totality in order to be consistent results within quantum mechanics and the correct description of reality. So theoretically, we get answers to our questions by processing the wave function. So experimentally, we make different kinds of measurements, or theoretically, to anticipate those experiments, we ask questions by answer questions by processing the wave function. For example, if we're talking about a particle, if we want to answer questions about its position, we process the wave function in one way. For mathematicians and physicists, we square the magnitude of the wave function. While to answer questions about its momentum, we must process it in quite a different way. We have to take its Fourier transform and then square the wave function, which is quite a different and much more complicated operation. The wave function, going back to ordinary language, the wave function is like a block of marble which we can sculpt into different shapes, or a visual scene which can be rendered from different perspectives or in different styles, or a musical piece that could be played in different instruments. And each way of processing gives the correct answer to an important question, but they're mutually incompatible. So the wave function, going back to the analogy of a block of marble, we can sculpt it either to make a rabbit or to make a duck, if we're interested in knowing what a rabbit looks like or what a duck looks like, but we can't do both at once. That's how complementarity shows up in quantum theory, where it's a rigorous theorem that different kinds of questions can't be posed and answered at the same time because they involve different ways of processing reality. So now I'd like to, yes?
Yeah, I would like to ask, does that mean that science, by finding this thing, has found its own limits, but at the same time liberated us from thinking this wrong either or way?
Yes, I think that's correct.
It's complementary.
At the same time, it exposes limits, but it exposes limits in a very wonderful way, because the limits are not limits to what you can ultimately do, but sort of limits to what you can do all at once. You have to ask different kinds of questions, and it's also an encouragement, showing that different points of view can each be valid in its own terms as its answer to its own kind of questions, even though they seem to be mutually incompatible. So now, with that kind of idea in mind, let me discuss very briefly other candidates for complementary thinking, having shown that it's an aspect of our perception of the world, of how we think about the world, and of physical reality, especially in quantum theory. So one complementary pair that Bohr, who liked to make jokes, often talked about, is that he said that clarity and truth are complementary. So your statements can be either clear or true, but not both at once. And we have a figure that embodies this kind of complementarity. It's the spherical cow. So A cow is very complex, and to answer some kinds of questions about it, to render it truthfully, you have to have a very complex figure. But if you want to be clear and simplify the description so that you can do calculations and make certain deductions, then it's easier to deal with a spherical cow. The topology is accurate, right? You haven't torn the cow up in any way, so you haven't ripped it. You've changed its geometry, but it's not its topology. So that's very good. So it's still a sphere or a ball if you take into it in its internal structure, but by continuous deformation, you can turn it into a real cow. Well, a toy cow. Another complementary pair that is very, very serious, I think, is and becoming very topical now as artificial intelligence becomes more powerful, is the complementarity of mind and matter. We think ordinarily and historically that mind and matter are very different things. People experience mind and matter in very different ways. And yet, computers and artificial intelligence are showing us that machines that we construct and we know the rules of, that are definitely matter, can think and exhibit things that seem to be very mind-like. And furthermore, as we've done very precise experiments in neurobiology using delicate tools that we have to make sure things are at the right temperature, at the right pressure, and shield from electromagnetic radiation, et cetera, et cetera. One thing we've never had to do is shield from thought waves. We get the same experimental results no matter what the guy in the next laboratory is thinking. And so there's also, from that kind of consideration, I think a lot of empirical evidence that mind emerges from matter, that it is a special property of matter. Now, this doesn't put down mind. Mind is still what it is, but it's another way of understanding it that brings different kinds of insights. It's a complementary view of thought processes and mind.
I have a question.
Yes.
You say in one of your books that the source of matter is pure energy.
Yes.
So,
Well, yes. Okay. That's a very good point. So.
well, I'm asking, could it be that consciousness is the fundamental thing, and matter becomes?
Yes. There may be a complementary way of viewing things, so that it doesn't have to be. That's the contradiction may only be superficial. It may be like for the duck and the rabbit, you can consider either as a duck or as a rabbit, and both are correct. In fact, in physics, recently, there's been increasing popularity and tendency towards the idea that we can describe the physical world in terms of information instead of in terms of things like mass and space and time that traditionally have been the basis of physics. This alternative viewpoint is very far from complete and still very speculative, but it's something that might emerge as a complementary way of viewing physical reality. I wouldn't say it was as consciousness as such, or maybe what we're learning what consciousness is as we elaborate these concepts. But in terms of information, we may be able to describe the world, the physical world, conceivably, in an alternative way that's just as accurate as the traditional description.
Isn't this just what you want to find out?
Well, I would love to find out whatever there is. Yes, it's a very fascinating perspective to think about. Let me emphasize that it's not yet realized, but it's a very, very inspiring kind of ideal that you can think of the world as accurately as we've learned to think about it in terms of concepts like mass, space, and time, there may be an alternative conception, which will not be contradictory, but just a different way of processing and presenting the material that is based on concepts of information. So a lot of us are working towards that. Another complementary pair is free will and determinism. It's not unrelated to what we just talked about. In the physical equations that we now know are very, very accurate description of all aspects of matter that are relevant to everyday life, I think, and engineering. We have what's called the standard model, which has been very well tested and with great accuracy in very extreme conditions, which seems to fully govern the fundamental behavior of ordinary matter with enough accuracy for any practical purpose. And the equations of that theory is definitely deterministic. There's no, if you knew the wave function and continued the equations, what happens is absolutely determined. On the other hand, we experience that we make choices, and let me pass to the jokes. So, for instance, here, I wanted to draw a comic about free will, but I decided not to. We all know that we could do that. You get to choose whether you make the picture or not, despite the equations. Or here, if someone is on trial and says, my wave function made me do it, the judge will probably not accept that as a defense. So we need this concept of free will. It describes a very important aspect of our experience, and it's necessary in our dealings with other people and society. And that's an important way of viewing the world. And yet, at the same time, we have an alternative description in terms of wave functions or the principles of the standard model that says that the evolution of things in time is determined. Another pair is complementarity and unity. This is captured to me beautifully in the Chinese Taiji or yin-yang symbol. You see, there are many possible ways to interpret this symbol, of course, but one way is that you're trying to describe reality, and it has different aspects. This is in line with the complementarity. So you can view it either as, well, take your favorite pair, either as free will and determinism, and both are aspects of a valid description of the whole of reality. And I think a beautiful feature of the Chinese symbol is that the eyes of these two fish, they show that within each description, you have implicitly also the possibility of the other interpretation. So they're not truly contradictory. It's just that one is easier to use in some circumstances to answer certain questions, and the other is appropriate to answer other questions. Finally, I'd like to go back and conclude this talk in somewhat dark times on a hopeful note that and going back to F. Scott Fitzgerald, with whom we started, another complementary pair is realism and hope. So let me complete the quotation that I started with. Remember, the test of a first-rate intelligence is the ability to hold two opposing ideas in mind at the same time and still retain the ability to function. And he went on to write, one should, for example, be able to see that things are hopeless, yet be determined to make them otherwise. So, thank you very much.
theater piece in Berlin called Parallel Worlds.
Oh, yes.
And there was a physicist talking there, and everything was very scientific. But my question to you is it wrong, basically, to think in terms of these subatomic quantum things when we talk about people in this scale of humans?
Well, it's a very, very long road from electrons and atomic nuclei to people. People contain billions of billions of billions of billions of protons and electrons. And when you put them together, they behave in very different ways from the individual ones, and we can't really solve the equations. So we have to use intermediate concepts. So I think, although there's no reason to doubt, people have done many delicate experiments, as I mentioned, there's no reason to doubt that the equations are still valid for describing a person. It's not a useful description if you want to write a love poem or understand what someone is going to do, what effect your actions will have. It's not very helpful to think of the person as a collection of atoms and molecules. On the other hand, if you want to cure their diseases, it may be very helpful to think of them as a collection of atoms and molecules and understand what's causing the bacteria or maybe the genetic defect, whatever causing the disease at a molecular level. It doesn't mean the person is not a person, or it's just, but it's a different way of thinking and answering different questions.
Now I have a question that really shows how ignorant I am, but what is a definition of a system? Because one atom is not a system, because I read somewhere that energy is...
Oh, no, a system is whatever you want it to be. So, so one aspect of our description of nature and of the world, because we know this description works, is that the action between different bodies is what we call local. That is, if we have an isolated body, it can be treated to a very good approximation as not by itself, without having to refer to distant objects. Now, this needs different kinds of qualifications, but that's the correct spirit of the thing. You can isolate, and you can isolate a big thing, or you can isolate a small thing. Whatever you isolate and want to think about as itself, without taking into account the rest of the world, you call a system.
Okay, because I read in one of your books that energy is not conserved in an individual particle, but in a system. Did I
Yes, you have to be sure to make your system big enough that is taking into account.
So where is the limit? Where is the limit of system or not system?
Well, as I
mean,
it's a matter of how much you want to keep track of, really. It's a practical matter. There's no fundamental distinction between a system and what's a system and what's not a system. So if you're willing to have a large enough view, a very large thing can be a system. The whole world, the whole Earth could be a system, or we talk about the solar system. But sometimes it's useful just to think about the Earth and forget about the rest of the solar system. Sometimes we have to bring in the sun. In everyday life, we think on a much smaller scale. We think about the people around us. When we're cooking, the system is the ingredients and the frying pan and the oven and things like that. So it's a flexible concept, and that's
okay, we have
an important aspect of complementarity is the ability to think in different ways about the same thing at the same. There's a question.
Yeah.
Yes.
Together. But when we are coming into applying those concepts to for example, sending a satellite and things like that,
Yes.
we really have to go and choose for one of these two opposite theories, don't you?
Yes, different theories can be different views can be much more convenient for answering the appropriate questions. So if you want to program a satellite to go in a certain place, you definitely want to use analytical equations that represent the satellite as a point-like mass that moves through space and obeys Newton's laws of motion. If you want to design the internal aspects of the satellite, that's quite different. Then you might want to think about the electronics that's inside. So for some points, for some questions you focus on one thing. For other questions you focus on another. But in some cases, as you say, one particular point of view may be overwhelmingly advantageous, and certainly for sending satellites into space, regarding them as objects that are simple and obey Newton's laws of motion is the right way.
So what we could learn from physics nowadays is a lot of tolerance for the diversity of ideas.
I think that's an important lesson we should take. That it's an overwhelming message from complementarity to me is tolerance, because different points of view can be superficially contradictory, but not deeply contradictory, and to do justice, to do full justice to reality, we should consider many different points of view.
Also in physics, which is
Yes.
So the reason why Frank Wilczek is here is that I saw him in television, in YouTube, and he was talking about beauty, always about beauty. So I was so, what? This is wonderful. And now to bring things together, what we have been talking about, I think there's something what Bach also did. He was not happy with his works. I mean, can you imagine? He was not happy. They were not symmetrical enough.
Right.
So when Frank Wilczek says that the standard model, which is one of the great achievements of mankind, it's still not beautiful enough. It's not beautiful enough to be God's last word.
Right.
So he's working on to make it more simple and beautiful. And I think this is what the world needs: beauty and simplicity and wholeness. Right? Complementarity. Thank you so much.
Okay, thank you.
Now we have some coffee.